So welcome back. This I promise will be the last lecture on Maxwell's theory and the special theory of relativity. So now we have all the the tensorial mechanism ready so that we can attack and write Maxwell's equations in a very pretty form. So using all the previous machinery, we can now write Maxwell's equations in a relativist, in a very pretty form. So what is it? It is, let me use red, del mu f mu nu is equal to mu naught j nu. Okay, where as we discussed before, f mu nu is del mu a nu minus del nu a mu. Okay, so this is the equation that I showed you previously, and some of you were curious as to how it came about, and so this is Maxwell's equations written out in this beautiful form. So just the fact that I've written it doesn't mean that you're going to believe me. So let me try and unpack this for you. Unpacking the equations. So remember, Maxwell's equations in the old form where what? Del dot E is equal to rho over epsilon naught. Del cross B is equal to mu naught J plus mu naught epsilon naught del E del T. Del dot B is equal to 0 and del cross E is minus del B del T. As you can see, the equations on the left, these are scalar equations. As in, there is no vectorial index left over. Left hand side is a scalar quantity, and the right hand side, of course, is also a scalar quantity. These, on the other hand, are vectorial equations. So if you count, so this is one scalar equation plus one scalar equation from the left, 3 scalar equations plus 3 scalar equations, so altogether of 8 scalar equations, right? Or let's say 8 equations. Okay, and also let's count what we have from here. So del mu f mu nu is equal to mu naught j nu. This also has, so there is a leftover index. So this is 1 4 vectorial equation, right? What has happened is the mu index has been summed over, so your nu is the one which is free. So nu is, that can take 4 values, 0, 1, 2, 3, and each of them will correspond to equation. So that's essentially so that is 4 equations. Okay, so there seems to be a mismatch. Maxwell's equations in the old form give you 8 equations. Our new swanky looking Maxwell's equations give us 4. So before we go on to solving this apparent problem, let's try and first figure out what these new swanky looking Maxwell's equations actually give you. Okay, so del mu, our equation is del mu f mu nu is equal to mu naught j nu. Remember, j nu is given by c rho and j vector. So let's start off with the 0th equation. Okay, so del mu f mu 0 is equal to mu naught j 0. So what is this? So this is what? This is del 0 f 0 0 plus del I f I 0 is equal to mu naught, and this is let's call this j. Sorry, this is c into rho. Okay, all right. Now, so this I is something which is a spatial index. It runs over 1, 2, and 3. Okay. F00 is of course 0 because F mu nu is antisymmetric. So you're left with del I F I 0 is equal to mu naught C rho. And this is what? This is del I into EI by C is equal to mu naught C rho. As you can see, this is nothing but del I EI equals to mu naught C squared rho. This essentially means that the divergence of the vector E is rho by epsilon naught. So this is Gauss law. Very good. So that's one. So the next one is going to be del mu f mu. So now nu is equal to I. Okay, let's say this is I. This is mu naught Ji. Okay, this is nu equal to 0. This is nu equal to I. So let's for the moment take nu equal to x. Okay, nu equal to 1. So let's look at this equation. So this is del mu f mu 1 is equal to mu naught j1. So what is this? Let's write this down. So it's del naught f01 plus del 1 f11 plus del 2 f21 plus del 3 f31 is equal to mu naught j1. So what is f01? What is del naught? Del naught is 1 over c del t, and f01 is minus Ex by C. F11 is 0 and so del 2 is del y. F21 is actually Bz plus del 3 is del z, and F31 is minus By. This is equal to mu naught J of X. Okay, that's right. So what do we get? So we get 1 over C squared with a minus del T of Ex plus del y Bz minus del z By is equal to mu naught Jx. This is nothing but minus mu naught epsilon naught del E del T, the x component of this, plus nothing but the curl of B, the x component of this, is equal to mu naught Jx. So if you do this for I nu equal to 2, nu equal to 3, you would get the y components and the z components. So at the end of the day, what you're going to get is that del cross B is equal to mu naught J plus mu naught epsilon naught del E del T. So this essentially is what is our Ampere's law. Ampere's law with, of course, the Maxwell correction. Right? So what we have seen is that the two of these guys, so del nu F mu nu equal to mu naught J nu, gives us Gauss's law and Ampere's law. Now what about the other two? What about the other two? Now you have to remember the fact that when we have defined F mu nu as del mu a nu minus del nu a mu. So in defining the potentials, we have already used the other two equations. Right? So what has happened is, for example, so these will be automatically satisfied. Del dot B is del dot curl of A, which is obviously equal to 0. So this is one which is, automatically satisfied. And remember the other one, that, E was given by minus grad of phi minus del A del T, which meant that when you look at the curl of E, you are going to get the curl of minus grad phi minus del A del T, which is nothing but minus del T of the curl of A, which is minus del B del T. So these things are automatically satisfied. These two equations are automatically satisfied because of the way that you have defined F mu nu. Okay. So. 。 So the other equations, so what I want to write down for you here is the other Maxwell's equation, other two Maxwell equations are automatically satisfied if you take into account F mu nu is del mu a nu minus del nu a mu. Now you could have envision a situation where you are not defining F mu nu directly in terms of A nus, but you're just saying that F mu nu is this matrix that we have been looking at. So we will say that F mu nu is this matrix here, and we are not thinking of this in terms of an underlying 4-vector A mu. If you are defining F mu nu like this, in order to get the other set of equations, the other two equations, you will need to define something else. So this is let me write this down first and then explain what exactly I have done. So one can define a dual electromagnetic tensor So this one is something we can call it G and upstairs mu. It's very bad notation actually. So let me actually do something. Let me not call it G. Let me call it F twiddle mu nu. And this one is this matrix 0 minus bx minus by minus bz bx by bz 0 ex over c minus ez over c minus ez over c. What am I doing? Excuse my mistakes. Ey over c minus ez over c 0 ex over c minus ex over c, and this is ey over c. Okay, this is something which is a dual electromagnetic field tensor, and this can be got, if tilde mu nu is obtained from F mu nu by the substitution E over C goes to B and B goes to minus E over C. This transformation should start to ring bells again. This is what exactly we saw when we were dealing with the electromagnetic duality that we had harped on before. And there is actually more to this, but we shall not go more deep into this. If any of you are interested, you can send me an email. I can send you some more references on where to read up on this. But the other two equations in this case can be formulated as del mu f tilde mu nu equal to 0. Okay, so this is so let me sort of reiterate the logic here once more. For what I said is, when you are looking at Maxwell's equations, this takes this pretty form of del mu f mu nu equal to mu naught j nu. And then when we unpacked this equation for nu equal to 0, this gave us the Gauss law, and for nu equal to I, this reduced to the Ampere's law. So it seemed that from in the old form of Maxwell, we had taken care of two equations, one here and one here. So we took care of these two equations, but the other two equations seem to have been left out. So how could one get these two equations here? So in order to get these two equations, we saw that this was already built into the system if you had defined f mu nu in terms of these four vectors a nu. If you had done that, this potential form of electromagnetism, so that related, so in a sense the definition of a nu itself came from these two equations of del dot b equal to 0 and the curl of E equal to minus del b del t. So these two equations are automatically satisfied if you take into account f mu nu is built out of these a nus. Okay. Now you could envision a situation where you are not defining f mu nu as del mu a nu minus del nu a mu, but you are simply saying that it's given by this matrix which has all the indices that we discussed before. Then you do not have this potential formulation anymore, and in order to get the other set of equations, you need to define a dual electromagnetic tensor f tilde mu nu, and that was given by this matrix, which interestingly can be got from f just by substituting E as B and B as minus E. This is the same as the duality transform that we saw earlier. So let's say f the electromagnetic duality transform. And in terms of this dual electromagnetic tensor that we have defined, the two equations above become del mu f tilde mu nu equal to 0. So if you are not using the potential formulation in that case, so let me again write this little bit down. I hope I don't confuse you with this. So if you don't use the potential formulation, then Maxwell's equations are del mu f mu nu equal to mu naught j nu and del mu f tilde mu nu is equal to 0. So here you do not assume f mu nu equal to del mu a nu minus del mu a mu. But you don't need to really worry about this. We are always here, and in advanced courses we always assume that f mu nu comes from a four potential formulation. So yeah, so if you wish, this last bit was a bit redundant. But so just to end, let me say that another thing that you should keep in mind is that your equation is del mu f mu nu is equal to mu naught j nu. So this is a vectorial equation, right? if this is a vectorial equation, remember that if you have under Lorentz transformations, a vector u, a four vector, a four vector, say z, goes to lambda z, right? So this is what we have seen. So if this is a four vector, so now you have a vectorial equation. So under Lorentz transformations, Maxwell's equations are not Maxwell's equations are not invariant, but they transform nicely. Now remember that if this z had z primed, z goes to z primed, so let's call this z mu. Z goes to z prime mu, which is lambda mu nu z nu. So if you have z primed 0, so this goes to lambda 0 nu z nu, right? So in this case, so let's just say that this goes to lambda 0 0 of z0 plus lambda 0 I of zi. So if you are thinking about so now this is an equation. So the left hand side of this equation is going to transform like a vector. The right hand side is going to transform like a vector. So you can think of this, you can think of this thing as so if you transform this equation. So if you transform, remember, if you took, so you can call del mu f mu nu minus mu naught j nu. So you can call this some vector b nu. Okay. So b nu is of this form, and so b naught is the del naught f. Sorry. Del mu f mu naught piece, and bi is the del mu f mu I minus mu naught ji piece. So this you can call as the Gauss law piece, and this you can call the Ampere's law piece. So what is happening is that if you were to give the vector b Lorentz transformation, it should be absolutely, evident from just looking at this line that Gauss law is going to go to Gauss law, Gauss law primed plus Ampere's law. So there is going to be a mixing between the pieces. So Gauss law under Lorentz transformations, Gauss law under Lorentz transformations goes into Ampere's law as well. This last bit may have been a little quick, but what I mean to say is that these Maxwell's equations are not invariant under these Lorentz transformations. They transform nicely. And if you were to take the first equation and explicitly perform a Lorentz transformation on it, you would see that Gauss law would actually go into Ampere's law. I leave this to you to try and work out in more detail. But as I said, you could define something which is B nu, and B nu equal to 0 is going to be the equivalent of Maxwell's equations, and you could see how these things transform. And it's very clear that when you go into another frame, since B nu is a 4 vector, in that other frame, the components of the 4 vector are going to mix up. B naught primed is going to go to B naught. So B naught primed is going to go to something lambda naught naught B naught plus lambda naught I Bi. So something which was the Gauss law to begin with becomes the some Gauss law plus the Ampere's law. So there's going to be mixing up of pieces, but the point essentially is that we are going to understand this. We would be able to understand the transformations, and all we have done is we have got things in a very nice vectorial form, such that when we are moving from one frame to another, we can keep track of what is happening, and we do not need to go back into trying to say that, okay, this is moving with speed v with respect to this frame here, and there is another frame that moves with respect to the second frame at rate v prime, and there is a Lorentz contraction in this frame and a Lorentz contraction in that frame. So all of those information, all the whole information is sort of packaged in a very nice form in your Maxwell's equations. Lastly, let's just quickly see another very nice thing here, is that if you look at del mu f mu nu equal to mu naught j nu, if you took another say you hit this with so this is Maxwell's equations. So let's say you hit the whole thing with a del nu, okay? So this object is what? This is mu naught del nu j nu. Now notice that the left hand side is del mu of f mu nu. So this part is symmetric, since partial derivatives commute. And you know that this part is antisymmetric. So anything that any two objects which are symmetric, if the multiplication of any two symmetric and antisymmetric objects always will give you a 0. So symmetric. So this particular thing is, so del mu f mu nu is always going to be 0. This you can again convince yourself by just writing this down. I will not do this here, but if somebody is not clear about it, what you can do is you can take some vector a mu nu, some tensor a mu nu, and if it's symmetric, then you can write it as a mu nu plus a nu mu, and you put a half out here. and if it says you have something which is b mu nu, which is antisymmetric, you can write it as b mu nu minus b nu mu. So a mu nu is symmetric, b mu nu is antisymmetric. So if you have a mu nu times b mu nu, you can show that this is going to be equal to 0. I'll leave this as an exercise. You just write this down as a nu mu and a half b mu nu minus b nu mu. And you can do some steps and you can show that this is equal to 0. So anything, that's symmetric times an antisymmetric guy is going to be equal to 0. So the upshot of this is, del nu of f mu nu is equal to 0. What does this mean? This automatically, del nu of f mu nu equal to 0 automatically implies del mu of j mu equal to 0. So what you see is, so this is, if you remember, this is going to be the continuity equation. So in this particular pretty form, Maxwell's equations just directly show you that, the continuity equation has to hold, okay? So this is a very, nice and elegant formulation of the Maxwell's theory. And you should remember this. And so the main thing that you should take away from this whole lesson of how electricity and magnetism fits in with the special theory of relativity is that these forces, electric and magnetic forces, are not separate things. There is only one thing, which is the electromagnetic force. And if you wish, if you really just knew electricity and you knew that there was the special theory of relativity, you knew that existed, then you would be able to find that there, in another frame, there is going to be another force that is going to be the magnetic force. So these things, Lorentz transformations, mix up what an electric force and what a magnetic force is. But at the end of the day, you can write down everything in a nice, pretty Lorentz covariant form, whereby we know how these things transform into each other, and we can write down Maxwell's equations in a nice vectorial form, which is very nice and which is very, very useful as well. So all those four equations, if you wish, now just boil down to one equation, which is just given by this del mu f mu nu is equal to mu naught j nu. So now that you have understood Maxwell's equations in this very nice form, and you have understood the very crucial role that relativity plays in this, you would be able to appreciate electromagnetism even more. So this is what we had to say about the special theory of relativity and the electromagnetic force. From the next class onwards, we shall be looking at other things. So in a sense, now that you have Maxwell's equations, all that is left to do is sort of solve second order differential equations given, partial second order differential equations given some boundary conditions. But we shall go into some of these applications, show you a little bit more about electromagnetic waves first up. And that is going to be what we would discuss in the next lectures. So next around 5 lectures will be on that, and then we will do a little bit of radiation as well. Okay, so that's it for now from me, and thank you very much. Bye bye.